Okay. Good morning, all. From last few lectures, we are discussing related to the cast irons and its different types, along with their composition properties, different applications, and for different cast irons, which microstructure they are having, or which phases are there in their microstructure that we are discussing. In that, we have finished the white cast iron, then malleable cast iron, gray cast iron, and high duty cast iron. We have studied up to this part. Now, in this lecture, we are going to deal with the remaining few types of the cast iron on the basis of their microstructure. In that, we are going to discuss the nodular cast iron. Then after that nodular cast iron, we are going to discuss the mottled cast iron, then chilled cast iron, and the last one will be alloy cast iron. Now we will start with this one, that is nodular cast iron. Okay, the first point, as usual, will be related to their composition. Now, uh, why these cast irons are termed as the nodular or ductile, or in bracket I have written one short form, that is SGCI, that is spheroidal graphite cast iron. And why this name is given to this cast iron type, that I will tell you. That is, these cast irons in their micro, if you observe their microstructure, here free carbon will be there, and this free carbon will present, or its shape will be spherical, or its shape will be like a nodule. That's why these cast irons are termed as nodular cast iron or spheroidal graphite cast iron, because graphite which is present here, it will be spherical in nature, or nodular, or nodule shape in nature. That's why it is termed as nodular cast iron, or it is also termed as spheroidal graphite cast iron. And due to the spherical nature of this graphite, these material will provide you high ductility and high toughness. Due to its high ductility property, these cast irons are also known as ductile cast irons. Okay, these cast irons are also known as ductile cast irons. Due to that spheroidal graphite present in this microstructure, it will provide you high ductility and high toughness. That's why it is termed as the ductile cast iron. And now, how these are manufactured? Now, as we have seen that malleable cast irons are manufactured from the white cast iron, then high duty cast iron or Muhonite is manufactured with the help of gray cast iron. In the same way, these nodular cast irons or ductile cast irons, these are manufactured or produced from the gray cast iron only. Okay, in composition, you can write composition of the gray cast iron, plus just you have to add a few nodulizing elements. Okay, there are certain elements which are termed as nodulizing elements. Nodulizing elements means which when added in that cast iron, they will turn whichever flex are there, flex shaped graphite is there, they will transform that flex shaped graphite into spherical shape. That's why, or that spherical shape is also termed as the nodule shape. That's why these elements are termed as nodulizing elements. And which are the nodulizing elements? Magnesium, calcium, barium, then lithium, zirconium, then cerium. All these are the nodulizing elements, and we are not going to add directly these elements in the gray cast iron. Okay, we are not going to directly add magnesium. We are going to add a compound containing that magnesium. Okay, you have to take care the related to this. That is, we are not directly adding this magnesium in it, but we are adding it in the form of a alloy or a certain compound. From that, it will get added to the that particular cast iron. And here we are using only gray cast iron. In gray cast iron, we are adding these nodulizing elements. Now, and when to add these nodulizing elements? First, you have to take that gray cast iron material, and you have to heat that gray cast iron material into the liquid form or molten form. And in that molten form, we are adding these elements in the form of their respective alloys. And after that we are going to do the pouring and remaining processes of the casting, and at the end you will get your desired product. Okay, in this way we are converting the gray cast iron into nodular or ductile cast iron. Then what changes will occur related to their properties? Now here this gray cast iron will get improved ductility, toughness, and improved tensile strength due to addition of these nodulizing elements. Spherical graphite will be there, and it will, due to that spherical nature, it will provide ductility, toughness, and along with that its tensile strength will get improved. Now the last point in this nodular cast iron is applications. These cast irons are widely used for manufacturing of crankshafts, then gears, then dies which we are using in the punching operation or sheet metal working operation, then different furnace doors, then pipes, pistons, cylinder blocks, and heads. And the bearing blocks are there. Bearing blocks means the blocks which carries that bearing, or where bearings are placed. That bearing blocks also are manufactured with the help of this ductile cast iron or nodular cast iron only. So this is the description or information related to the ductile cast iron. And after this ductile cast iron, the next type will be mottled cast iron. Please note down this information or this slide. Please make note of it. That is composition, properties, and some applications are there. At least note down the applications. Just you have what you have to note down from the composition point, the first point and third point, and property there is only one point, and the application. Please note down, and after that I will discuss the next type. Please mention in the chat box after completing. Okay, one more important point is there in this nodular or ductile cast iron. It is whenever you are taking the gray cast iron composition, you have to select the gray cast iron in such a way that the sulfur percentage should be less than 0.03%. Okay, why we are selecting the lesser sulfur, or also the phosphorus content should be very less? Because if sulfur or phosphorus amount is more, then what will happen, whichever that nodulizing elements we are adding, that elements will form another compound by reacting with the sulfur or phosphorus present in that cast iron. That's why its amount should be properly controlled, and it should be less than 0.03%. Okay. And after this nodular reductile cast iron, next type is the mottled cast iron. Please confirm that you have finished the writing. Okay. Then we will move towards the next type. So this is the mottled cast iron. Now, this mottled cast iron, it is very easy to remember it. This mottled cast iron is a combination of white cast iron and gray cast iron. Okay. Now, this mottled cast iron contains free graphite, or you can say that free carbon in the form of graphite, as well as it contains carbon in combined form, and it will be present in the form of cementite. Okay, in its microstructure you will able to find both phases, that is free carbon and combined carbon. Free carbon in the form of graphite will be there, free carbon in the form of graphite, and carbon in the form of combined form, it will present in the as a compound, that is the cementite. Now, for the formation or to get the mottled cast iron, you have to select cooling rate properly. Now, as we have earlierly discussed that whenever cooling rate is very fast, you will end up with the white cast iron. Okay, whichever microstructure is there, carbon will present in the combined form whenever faster cooling rates are used. And whenever we are using the slower cooling rates, carbon will get separated, then you will end up with the gray cast iron. Okay, carbon will present in the free form and in the form of graphite flakes. And whenever you are using the intermediate cooling rate, not so much slow or not so much fast, then at that time you will end up with the combination of white cast iron and gray cast iron. And whichever cast iron type is obtained, it will be termed as mottled cast iron. Okay. Then now, how to control the composition here, or composition, or that structures, means you should get the combination of white cast iron and gray cast iron. And that first is the selection of the cooling rate. You have to select the intermediate cooling rate. And another way is by controlling the composition. Now, in which way you can control the composition? If suppose you have taken gray cast iron, then by increasing the amount of carbon and silicon, by increasing the amount of carbon and silicon, by increasing amount of carbon and silicon in gray cast iron, or by decreasing the amount of carbon and silicon in the white cast iron, you will end up with getting the mottled cast iron microstructure. Now, as it is a combination of white cast iron and gray cast iron, the properties will be in the means combined properties will be there. But as far as our practical use is there, these are not so much preferred. Instead of using this mortar cast iron, we can use the chilled cast iron. And why we are using the chilled cast iron, that we will discuss after this completing this mortar cast iron. Just try to remember this for lots of practical applications. We are using chilled cast irons, which is having combination of this white and gray cast iron. Then here mortar cast iron will be having very high hardness and wear resistance, very high hardness and high wear resistance. And its applications I have shown here. In the mottled cast iron is used in the manufacturing of mill rolls. Okay, whichever rolls we are using here, these mill rolls are there. These mill rolls are manufactured with the help of mottled cast iron. Here I have shown that diagram for that mill rolls. These are manufactured with the help of mottled cast iron. Okay, so this is the mottled cast iron, combination of white and gray cast iron. And here its distribution of that white cast iron means cementite, and gray cast iron means that graphite flakes. It will be not uniform. Okay, it will be not uniform. At some places white cast iron, at some places gray cast iron will be present. Okay, that is the mottled cast iron. And due to this, in some type of the mottled cast iron, or sometimes you will end up with the very high brittleness also. That's why we are not using it for more applications. Only some specific applications are there, like mill rolls. Now, after this, the next type of the cast iron is the chilled cast iron. Okay, here also the chilled cast iron, you will find that here combination of white cast iron, means in the cementite phase will be there, and combination of gray cast iron will be there, that is free graphite will free carbon in the form of graphite will be there. But here, the presence of that cementite or white cast iron and presence of that graphite, it will be at the specific regions only. Means at the center of your component, graphite will be there. At the center or core of your component, graphite will be there, and on the surface of your component, cementite will be there. Means white cast iron will be present. White cast iron structure will be on the surface of that component, and at the center, gray cast iron structure will be there. That's why its surface becomes very surface of that component will provide you high hardness, then high wear resistance. And due to presence of graphite at the center, it will provide you, that material will provide you very good damping capacity and very good machinability also. It will provide you very good machinability and very good ductility or toughness at the center. Then related to its composition, these cast irons, these cast irons contains carbon percentage 3.3% to 3.35, silicon 2 to 2.3, with addition of some alloying elements, and remaining will be iron. Now, here, as we have discussed that on the surface only that white cast iron is there, means there, that white cast iron at the surface is obtained by doing the cooling with very faster cooling rate. And this cooling is used, or this cooling is done by using the chillers or chill plates at the surface of that component. Okay, and whichever depth is obtained having that white cast iron at the surface, that depth will be termed as the chill depth. We are doing the faster cooling of the surface by using the different chillers or the chill plates, and the depth obtained of that hardened surface will be termed as the chill depth. And this chill depth is controlled by using the certain elements. Means if there is change in the carbon, silicon, or certain other alloying elements are there, which act as a graphitizer, means they will increase the carbon or decrease the carbon depending on that chill depth will change. Okay, and certain parameters are there, like whenever you are using the carbon amount, silicon amount, or graphitizers amount, what will happen? A decrease in the chill depth will occur. Means it will try to improve the graphite amount only. That's why gray cast iron will be formed. Okay, and whenever carbon amount, silicon amount, and other graphitizing elements amount is decreased, then you will end up with getting the better chill depth or better hardness on the surface. Okay, better hardness on the surface. So this is related to the composition and phases present in this chilled cast iron. And as you are seeing that in the chilled cast iron, on the surface we are having white cast iron, means phase present is the cementite, and at the center we are having gray cast iron, that is carbon is present in the form of graphite flakes. Then due to this, what will happen? Whichever surface of component is there, it will be having high hardness and high wear resistance. And in at the center, due to presence of that graphite flakes, that material will provide you better toughness and better machinability. Now, the next point is related to the applications. These cast irons are widely used for manufacturing of railway freight car wheels, then crushing rolls, grinding balls, then road rollers, and different types of hammers and dies. Now, what is the meaning of this railway freight car wheels? Okay, certain that railway freight car wheels are there. Okay, for carrying, railways are there to carry the goods from one place to another place. That railway freight wheels, car wheels, whichever wheels are there present, these wheels, these are manufactured with the help of chilled cast iron. Okay, on the surface it will be having high hardness and high wear resistance. Okay, there will be more material loss due to the friction between the track and these wheels. To avoid that, we require the surface which is having high wear resistance and high hardness, and at the center to carry the large amount of load. To carry the large amount of load at the center, this wheel should possess the more ductility and toughness. It will be provided by that graphite present, and on the surface cementite, it is white cast iron is present. It will provide you hardness and wear resistance required. Okay, so these wheels, railway freight car wheels, these are manufactured from the chilled cast iron. Then these are the crushing rolls. Whichever waste materials are there, we are going to crush in this. Okay, some crushing rolls are there to crush the material. These whichever crushing rolls are there, these crushing rolls are also manufactured with the help of chilled cast iron only. Then next application, some dies are there. Okay, these dies are also manufactured with the help of this chilled cast iron. Chilled cast iron dies are used. Then different types of hammers are there. These hammers are also manufactured with the help of these chilled cast iron. Okay, so these are the few applications of the chilled cast iron. Then after this chilled cast iron, the last type of the cast iron is alloy cast iron. Alloy cast iron. Now, as in general, whichever types, up to this we have studied, 6 7 types we have studied. All these types are having lower impact resistance, then lower corrosion resistance, or lower temperature resistance. Means whenever we are using these material, we cannot use this material at the higher temperature ranges. So to improve the impact resistance, corrosion resistance, oxidation resistance, or temperature resistance, so that we can use these castons at the higher temperature applications also, we are going to add the certain alloying elements like nickel, chromium, molybdenum, vanadium, copper, silicon in the existing cast iron only, in the white cast iron or in the gray cast iron. We are going to add these alloying elements to improve their certain properties like impact resistance, oxidation resistance, corrosion resistance. And we are going to achieve this by addition of certain alloying elements like nickel, chromium, molybdenum, then copper, silicon in the white cast iron or in the gray cast iron. And whichever new type of cast iron is formed, that type of cast iron will be termed as the alloy cast iron. Okay, this alloy cast iron is nothing but white cast iron or gray cast iron with addition of alloying elements like nickel, chromium, vanadium, molybdenum. Like these elements will be added to get improved corrosion resistance, impact resistance, and whichever cast irons are formed, that will be termed as the alloy cast irons only. There may be number of alloy cast irons obtained, but a few generally used examples I have taken here. That is nickel hard cast iron. Then you can say that nickel resist cast iron. Then silal and nicrosilal. These are few examples of the alloy cast iron. Now we will discuss one by one along with their certain composition, their properties, and their few specific applications. We will start with the nickel hard. Now, as from the word itself, this nickel hard means we will be end up with the more hardness and more wear resistance. And from name itself, we will get that as nickel hard is written here, we are going to add the alloying element nickel in that particular cast iron. And here we are going to add that nickel in the white cast iron. In the white cast iron. hardness and wear resistance of that white cast iron is increased by addition of nickel and chromium, and also it will improve the toughness of that white cast iron along with the increasing in the hardness. Somewhat slightly change in the toughness will also occur. Now in the microstructure point of view, it contains martensite and austenite. This part I have given you for the information purpose. Sometimes they may ask you these questions like the microstructure related questions in the competitive examinations like gate also. That for nickel hard, it will contain the martensite and austenite. Due to this hardness, high hardness and high wear resistance is due to presence of this martensite phase only. Okay, due to this martensite phase only, it will provide you high hardness and wear resistance. Then its general composition in the white cast iron, its composition will be like this. You can directly write in white cast iron, in white cast iron, 3 to 5% nickel and 1 to 3% chromium we are going to add, and it will be termed as nickel hard cast iron. Sometimes we are going to add in the same white cast iron 4 to 8% nickel and 4 to 15% chromium. It will be termed as modified nickel hard. Okay, it will be termed as the modified nickel hard. Now after seeing these different compositions, what related to the properties already we have discussed that, that is it will be having very high hardness and high wear resistance. But as hardness and wear resistance is more, its fatigue resistance or its impact resistance is very less. Certain applications are there like grinding balls, then mill liners, then pulverizers rings, roll heads, slurry pump parts are there, then pipes, elbows, then different metal working rolls are there. All these are manufactured with the help of this nickel hard cast iron. It is a type of the alloy cast iron. Now after this, the nickel hard, just you have to try to remember which elements we are adding in the which type of the cast iron. Here in the white cast iron we are adding the nickel and chromium, and its percentage is nickel is 3 to 5% and 1 to 3% chromium. And in some modified type of the nickel hard, we are adding more amount of the chromium. More amount of the chromium is there. Now why we are adding the more amount of the chromium? Because whenever we are using the less amount of the chromium, it's what you can say that somewhat brittle, more brittleness, or you can say that strength is there, but it is not having the ability to absorb the shocks. But whenever amount of chromium is more, it will provide you the more amount of the carbides, and which will result in the more strength by reducing that brittleness. Means it can absorb some more shock also, means impact resistance is improved. What is the difference between this nickel hard and modified nickel hard? This modified nickel hard will provide you somewhat better impact resistance also, and due to formation of the more respective, the more chromium carbides are formed, and it will provide you the higher strength and higher impact resistance values. Now after this nickel hard, the next type is the nickel resist cast irons. Now as from the word itself, nickel resist, here we are going to improve the corrosion resistance. And here we are adding nickel and chromium, same elements are added, but now we are adding nickel and chromium alloying elements in the gray cast iron or in the nodular cast iron, so that its corrosion resistance will get improved. And whenever you are observing the microstructure of this type of cast iron, means in the gray cast iron or nodular cast iron, we are adding the nickel or chromium. And if you observe its microstructure, you will find that only austenite phase will be there. In the nickel hard, martensite and austenite phase is there. Due to that martensite, you are getting the higher values of the hardness, but here only austenite is present. That's why these cast irons are also known as austenitic cast iron. Only austenite phase is there. Now what about the composition? In the gray cast iron, we are adding the higher amount of nickel from 14 to 36% nickel, and chromium 1 to 5% chromium is added. And in some specific types, we are adding copper also. In some specific types, we are adding the copper also. Then what about the properties? Already I have explained that in the first point itself, that is they will provide you the better corrosion resistance, and also it will end up with the higher heat resistance. Means you can use this type of cast irons now at the higher temperature ranges also, and its wear resistance will be fairly good, not as better as the previous nickel hard cast irons, but it will provide you the fairly good values for that wear resistance and scaling resistance. And then for the application parts, these nickel resist cast irons can be used for manufacturing of the generator and motor covers, then pump bodies, whichever body is there in the pumps we are using, then manufacturing of the impellers and different valves, then exhaust manifold. Exhaust manifold is there. I have that diagram of that exhaust manifold. I will show you later. Then sewage pipes and cylinder lines are there. That all these are sorry, these are cylinder liners are there. By mistake, I have written here lines. Please read it as liners. Cylinder liners are there. And that cylinder liners will be manufactured with the help of the nickel resist cast iron. Then after this nickel resist cast iron, the next is the silal and the nicrosilal type. Silal and the nicrosilal. Now what is the silal? This silal is the type of the alloy cast iron. The low carbon cast irons, in the low carbon cast iron, 5 to 7% of the silicon is added. Okay, and you will end up with the ferrite plus graphite, fine graphite in the microstructure. That is the silal. And what is the nicrosilal? In the nicrosilal, in addition to this low carbon cast irons with silicon, we are adding nickel and chromium. This nickel, that's why for Ni for nickel and Cro for this chromium. That's why it is termed as nicrosilal. In silal, we are having low carbon cast iron with addition of 5 to 10% silicon only. And in nicrosilal, we are in this silal we are adding the nickel and chromium. So I have taken here composition of nicrosilal. This is the total composition, will indicate the nicrosilal. And silal, in this silal material, we have to eliminate this nickel and chromium element. Okay, this is the approximate composition of silal and nicrosilal. And what will be the changes in the properties? Now this material will provide you the better oxidation resistance and better heat resistance. Means you can use these cast iron types at the higher temperature ranges. And due to these properties, better oxidation resistance and better heat resistance, there are certain applications of the silals and nicrosilals, like exhaust manifolds, gas turbine, different components of the gas turbine, then aluminum melting crucibles, then glass molds and retorts. I will show you some diagrams of the applications. Now exhaust manifolds. Okay, this is the diagram for this part. Okay, please try to understand this part. This is the exhaust manifold. This is the exhaust manifold, and this is manufactured with the help of this silal. Okay, you can use silal or nicrosilal. Then different molds are there. Molds which are used for manufacturing of the glass bottles. different glass bottles are manufactured, and whichever mold is used for manufacturing of that glass bottles, that mold is manufactured with the help of this silal material only. Okay, this is the glass mold. This is the exhaust manifold. This is the exhaust manifold. Then glass molds which are used for manufacturing of the glass bottles. Then this is the different crucibles are there, melting crucibles. Okay, for melting the aluminum material we are using different crucibles. These all crucibles are manufactured with the help of this silal material only, silal, or you can use micro silal also. Then this is the retort. Retort is the equipment which we are using in the chemical labs. Okay, chemical labs, this retort equipment is used. This is manufactured with the help of this silal and or nitrosilal material only. Now for which purpose this retort is used? This is used for doing the distillation process. Distillation process is nothing but we are removing the different compounds from the liquid. From liquid we are separating the different substances. That process will be termed as the distillation process, and for that equipments are used in the labs, and that equipments are termed as retorts. And these retorts are manufactured with the help of silal or nitrosilal only. So these are the few applications of the cast iron. Okay, now in this way we have completed this second chapter, that is study of the ferrous material and its alloys. In this way we have completed this chapter. Now whichever part I have already discussed the classification of the plain carbon steels and cast irons. Now in some examinations they are asking you the microstructure. Compulsory one question will be there on the microstructure. Either they will ask you the microstructure of the any two or any three types names they will provide you, and they will ask you draw the microstructure for four, minimum 4 marks or maximum 6 marks will be there. Either they will ask you from this six means these are for the carbon steels, these are plain carbon steel diagram. These are only plain carbon steels, only just I have added one tool steel here. And for there will be four types, from 6 to 7 types are there for that cast iron. But out of that seven, they will ask you the microstructure related to this four types only. Now we will discuss about these microstructures. Just now we have completed the cast iron discussion, that's why I will explain this slide first, whether it is visible clearly or I have to zoom it. I will try to zoom it. Okay. Okay. So this is the microstructure of a cast irons, and from that the first diagram is for gray cast iron, and second diagram is for white cast iron. Now in the gray cast iron, as we have clearly discussed, that it consists of the free carbon in the form of graphite, whichever dark flex like structure, this flex like structure, these are the graphites. Okay, random orientation is there. Random orientation means different sizes flakes are present, and remaining amount will be ferrite and some amount of pearlite will be there. Okay, whichever bright spots will be there, bright spots, that will be ferrite, and this flex like dark spot will be graphite, and remaining dark portion will be pearlite. Okay, remaining dark portion will be pearlite. Large amount of graphite will be there. Okay, large amount of graphite will be there. So this is the microstructure for gray cast iron. Then this is the microstructure for white cast iron. Now here white, in the white cast iron two phases will be there, dark phase and bright phase. Whichever bright phase is present, that bright phase will be of cementite, and whichever dark phase is there, that dark phase will be of pearlite. And due to this cementite only, it will be termed as white cast iron. Okay, bright phase and dark phase, you will get the better understanding when we will see the microstructures in practical work. From that you will get the clear idea. That's now just try to understand whichever phases are there in gray cast iron. Flex graphite will be present in the form of flex, or graphite flex will be there, and remaining portion, whichever bright phase is there, that will be ferrite, and dark phase will be pearlite. Here only two phases are there, dark phase will be pearlite, and whichever white or bright phase is there, that is cementite. This is the white cast iron. Now the combination of these two, graphite and cementite, that will be your, you can say that, mottled cast iron. This is the gray colored graphite, that is, you can say that, gray cast iron, and remaining white or cementite will be there, that will be termed as white cast iron. This white cast iron is nothing but cementite phase, and gray cast iron is nothing but carbon in the form of graphite phase. This is the mottled cast iron. Then the last microstructure is nodular cast iron or ductile cast iron. This is the ductile cast iron. This center or spherical nodule shaped graphite is present in the form of nodules. The center dark round will be termed as the graphite. Carbon is present in the form of graphite, and it is in the nodular or spherical shape. This is the graphite. Then this its surrounding region will be having little bit bright color, and that will be termed as ferrite. This bright color around this dark circle, some bright color will be there, that will be a ferrite phase, and remaining dark phases which are surrounding these nodules, it will be a pearlite. It will be a pearlite. Main phase is this node. Graphite is present in the nodular form or spherical form. That's why it is termed as nodular cast iron, or it is also known as SGCI, that is spheroidal graphite cast iron. Spheroidal, that is spherical graphite. Okay, this is the microstructure of this nodular cast iron. So in this way we have discussed the microstructure of these four types of the cast irons. Now after this, we will discuss the microstructures of this, some types of the steels. Okay. Now these are the microstructures of the steels. Now in this first two diagrams, these are for what you can say that low carbon steels. Okay, these are low carbon steels. Here in bracket I have mentioned that carbon is present at very less amount, 0.05%. Now whenever carbon percentage is very less, its microstructure will appear like this. More bright spots will be there, and some dark spots are there, some dark phases are there. Okay, whichever bright phases are there, it will be ferrite or your alpha phase. Bright phase is alpha phase, and some dark spots are there, these dark spots of pearlite. Okay, pearlite is nothing but a mixture of ferrite and cementite, but it will appear in the dark color. This is a pearlite. And whenever percentage of carbon is less, ferrite percentage will be more. Okay, for example, this dead mild steel, it is having very less carbon percentage, 0.05%. Then the ferrite is almost more than 95%, and 3 to 5% only pearlite. And as carbon percentage increases, suppose carbon is 0.1 or 0.2, then ferrite will be 75 and 25% will be pearlite, that is the dark phase. Now we will suppose we move towards the medium carbon steel. In that medium carbon steel, carbon will be in the range 0.3 to 0.6. At that time, what will happen? Ferrite will be 50% and pearlite will be 50% for medium carbon steel. Low carbon steel, whenever low carbon steel is there, ferrite amount is more and pearlite is maximum 25% and remaining will be ferrite only. In medium carbon steel, 50% ferrite, that is the bright phase, and 50% pearlite, that you can show by the dark phase. Same structure you have to draw, just you have to increase this dark portion. And then you can say that 50% is pearlite and 75 and 50% is the ferrite in the medium carbon steel. For low carbon steel, ferrite will be more, that is bright phase will be more. And if carbon percentage is very nearer to the 0.008%, then ferrite amount is 95 to 100%. In that range you can vary. These are approximate values. Okay, it is 95, but it should be at the higher ranges. In low carbon steel, ferrite will be more and pearlite will be in very small quantity. As carbon percentage is increasing, ferrite quantity will goes on decreasing and pearlite quantity will goes on increasing. Then for medium carbon steel means 0.3 to 0.6% carbon is there. Ferrite and pearlite 50% will be there. And in the high carbon steel, in the above 0.6%, at 0.8% carbon, at 0.8% carbon, only one phase will be there, that is pearlite. As carbon percentage is increasing and it is moving towards 0.8, ferrite will goes on decreasing and pearlite will goes on increasing. And at 0.8% carbon percentage for this high carbon steel, 100% pearlite will be there. And if carbon percentage is 0.008, 100% ferrite will be there. At higher range, 100% pearlite, that is 0.8%. And for 0.008%, 0.008%, there will be only ferrite, only bright phase, just the bright phase will be there. Now in between this, somewhat point below this 0.7, you can say that only 5 to 10% ferrite and dark phase will be there up to 90 to 95%. And when carbon goes above this 0.8, above this 0.8, now 100% pearlite is there in the 0.8. When above this 0.8 carbon percentage is there, some amount of cementite will be formed. Suppose 0.9% carbon is there. Then pearlite phase is there, this dark phase, and bright phase will appear, that is the cementite for 0.9% carbon. Exactly for 0.8%, 100% pearlite is there. Okay, 100% pearlite is there. And for medium carbon steel, 50% pearlite and ferrite is there. Above this 0.8, whichever carbon percentage is there, pearlite and cementite will be there. Amount of pearlite will be more and amount of cementite will be lesser. For example, 0.9% carbon steel, that is high carbon steel, dark phase pearlite is there, which is presented approximately 90%, and 10% will be cementite. So this is the microstructure related to the low carbon steel, medium carbon steel, and high carbon steel. For medium carbon steel, 50% ferrite bright phase and 50% pearlite dark phase. When carbon percentage is less for low carbon steel, try to remember this structure only. If carbon percentage is very less, just increase the amount of ferrite and decrease the amount of pearlite. And when carbon percentage is at the higher ranges, increase the pearlite. And at 0.8% carbon, 100% pearlite will be there. You have to remember this. 0.8% carbon, 100% pearlite. And for lesser values, that is 0.008, 100% ferrite will be there. And in between that values, you have to, according to this percentage, you have to write ferrite, pearlite, then more percentage will be there, then pearlite and cementite for high carbon steels. Okay. Then for tool steels, this is the tool steel. In this tool steel, uh, perlite will be there. Perlite will be there. That will be a dark phase, and some bright spots will appear there, and that will be their respective carbide. It may be for any type of the tool steel. Perlite phase will be there. In that perlite, dark phase will be there as a perlite, and in that some bright spots will be there, and that bright spots will be of carbide. It may be chromium carbide, or it may be another carbides which are formed by another vanadium, molybdenum, whichever alloying elements you have added in that tool steel. Depending on that, carbides will be there. Sometimes they may ask you the microstructure of tool steel. Just you have to draw one circle in that dark phase perlite, and some spots you have to show bright spots, and that will be termed as the alloy carbides bright spots. Okay, bright spots are there. So this is the microstructure of the plain carbon steel and alloy steel. In that we have discussed about the microstructure of low carbon steels, which consists of bright phase ferrite and dark phase pearlite. When carbon percentage is lower, amount of ferrite will be on the higher side. For example, 0.1% or 0.2% carbon, 75% ferrite and 25% pearlite. When carbon is very less, then above 95% ferrite will be there, and pearlite will be 3 to 5% only. Then when carbon percentage is on the higher side, pearlite amount will be more. That 0.8% carbon, 100% pearlite is there. And when it goes, carbon percentage goes above zero point 0.8, pearlite plus cementite will be there. Pearlite plus cementite. And in medium carbon steel, means within the range 0.3 to 0.6, just you have to draw the same structure, and 50-50% ferrite and pearlite you have to show there. So this is the microstructure of uh, low carbon, low carbon, medium carbon, and high carbon steels. And along with this tool steels, in the tool steel, dark phase pearlite and bright phase of respective carbides will be there. Okay, in this way we have discussed the microstructures of the plain carbon steels, alloy steels, and microstructures of the cast irons, different types of the cast irons. In this way, this chapter, second chapter is completed. First and second chapter is now completed. First chapter is related to the introduction and the different types of the phase diagram, and second chapter, that is study of the ferrous materials and its different alloys. In that we have discussed the iron iron carbide equilibrium diagram, then different effect of the alloying elements, classification of plain carbon steels, then different types of the alloy steels we have discussed. In the alloy steels we have discussed different types of tool steels, stainless steels. Then after that we have completed different types of the alloy steels. Some specific alloy steels are there, like HSLS steel, silicon steel, maraging steel, like that. And after that we have discussed the cast irons, different types of the cast irons, and all this part we have discussed with related to their composition, properties, different types, and their different applications. And at the end we have also discussed about the microstructures of the plain carbon steel. In that microstructure of low carbon steel, medium carbon steel, high carbon steel, and microstructure of some alloy steels also. And after that we have discussed the microstructure of four cast irons, that is microstructure of gray cast iron, white cast iron, mottled cast iron, and nodular cast iron. In this way we have completed our two chapters. From next lecture we will start the third chapter, that is study of the non-ferrous metals and their alloys. Now in this way we have completed this chapter. If you are having any query, if you are having any query, you can ask me related to the steels, cast irons, or alloy steels, or related to the first chapter also. You can ask any query to me. In this way, we have completed this part, that is the cast iron. Okay. If you're having any query, you can ask me. Otherwise, I will stop these sessions. You can ask me queries. I will stop the recording here only. You can ask me queries. Okay. Thank you.